Array 15, 2022, 100242. Quantum cryptography. Algorithms standardization and performance analysis. Ish Kumar, Department of Master of Computer Applications, M.S. Ramaiah Institute of Technology, Bangalore, 54, India. ICLEINO. Words. Postquantum cryptography. Gauss-laced cryptography. Muckuriate quadratic equations-based. Cryptography. PKASC. Cat-based cryptography. MEC-based cryptography. ABSTRACT. Quantum computer is no longer a hypothetical idea. It is the world's most important technology, and the race among countries to get supremacy in quantum technology. It is the technology that will reduce computing time from years to hours or even minutes. The power of quantum computing will be a great asset for the scientific community. However, it raises serious threats to cybersecurity. Theoretically, all the cryptography algorithms are vulnerable to attack. The practical quantum computers, when available with million qubits capacity, will be able to break nearly all modern public key cryptographic systems. Before the quantum computers arrive with sufficient qubit capacity, we must be ready with quantum-safe cryptographic algorithms, tools, techniques, and deployment strategies to protect the ICT infrastructure. This paper discusses in depth the global effort for the design, development, and standardization of various quantum-safe cryptography algorithms, along with the performance analysis of some of the potential quantum-safe algorithms. Most quantum-safe algorithms need more CPU cycles, higher runtime memory, and a large key size. The objective of the paper is to analyze the feasibility of the various quantum-safe cryptography algorithms. Introduction. Cryptography is one of the most important pillars of cybersecurity. Cryptography is an art of rendering techniques and the science of protecting the information, where the information can be interpreted only by the sender and intended recipient. Most modern cryptography algorithms are based on complex mathematical functions. The design of cryptographic algorithms is based on assumptions of computational difficulty. These are asymmetrical problems, such as integer factorization. Multiplying two integers is straightforward, but factoring a 1,000-digit integer is difficult. Form of cryptography that uses two related keys, a public key and private key. The two keys have the property that, given the public key, it is computationally infeasible to derive the private key. Current public key encryption relies on the fact that a classical computer can easily multiply large prime numbers but requires thousands of years to reverse a calculation. Quantum computing will accelerate the ability to decrypt information protected by current public key encryption techniques. Quantum computing is a technology based on the principles of quantum theory, which is much faster than classical computing techniques. The classical cryptography algorithms are completely vulnerable to quantum computers. Transitioning to the quantum computer will make the existing IT infrastructure completely unsafe, and it requires design and development of quantum-safe or quantum-resistant cryptography algorithms. The objective of this paper is to discuss various cryptography techniques and potential quantum-safe cryptography algorithms, along with the performance analysis of the algorithms. The paper is divided into 8 sections. Section 2 gives general information about cryptography, followed by Section 3 introducing quantum computers. Section 4 discusses the post-quantum encryption problem. Many countries and professional organizations are putting effort to standardize the quantum-safe algorithms, which are discussed in Section 5. The National Institute of Standards and Technology, NIST, has initiated an intensive process to standardize the post-quantum encryption algorithm. Some of the potential quantum-safe algorithms which are announced by the NIST in third round of the selection process have been discussed in Section 6, along with the performance analysis of the algorithms based on the Open Quantum Safe (OQS) implementation. The overall observation, implementation feasibility, migration challenges are discussed in Section 7, followed by a conclude remark in Section 8. Email address, manishkumarjsr@yahoo.com. Contents lists available at Science Direct, Array, Journal homepage, www.sciencedirect.com/journal/array/doi0016/j.array.2022, date ed. April 2022, received in revised form 4 August 2022, accepted 4 August 2022.
Array 15, 2022. Cryptography, the building blocks of information security. Today, information security without cryptography is unimaginable. Cryptography is used in various ways to protect the confidential and integrity of the information. Information security hardware and software products implement cryptography in many creative ways, the sole purpose of providing security. Cryptographic algorithms are well-defined procedures or sequences of rules or steps, or a set of mathematical equations used to describe cryptographic processes, such as encryption, decryption, key generation, authentication, signature, etc. Cryptographic algorithms are broadly classified into two categories, namely symmetric cryptographic algorithms and asymmetric cryptographic algorithms. Symmetric cryptography algorithms. In symmetric cryptography algorithms, the sender and receiver use the same key to encrypt and decrypt the data. Symmetric key algorithms are very efficient and easy to implement. However, key management in symmetric cryptography is a challenging issue. The key must be shared among the two parties before initiating the communication. Symmetric cryptos are mainly susceptible to chosen plaintext attack, known plaintext attack, linear cryptanalysis, and differential cryptanalysis. Asymmetric cryptography algorithm. In an asymmetric cryptography algorithm, the sender and receiver use a pair of keys. One of the keys is kept secret, i.e., called a private key, and the other is made public, called the public key. An asymmetric cryptography algorithm is also known as a public key algorithm. The sender encrypts the data using the public key, and the receiver decrypts the data. Fig 1, Quantum Computing Growth in Qubits between 1998 and 2021. Fig 2, Qubit Timeline Estimate, source Gardner 83.
Array 15, 2022. Private key. Generally, asymmetric cryptography algorithms are security services. The public key ciphers are mainly vulnerable, chosen ciphertext attacks, man-in-the-middle attacks, and specific attacks related to the underlying hard problems. Symmetric and asymmetric, both the algorithms are vulnerable. Brute force attack 3575. In a brute force attack, the attacker tries all the possible keys. The resistance of the algorithms depends on the size and computational power required to generate and apply a possible keys to break the encryption. 22, 81, 84. Cryptography does not only secure the data, but is also used for confidentiality, authentication, integrity, and accessibility. The various implementations of cryptography algorithms in our daily life, for example, the use of SSL/TLS to provide secure internet browsing, digital signature for authentication and validation, electronic mail, transactions, secure data storage, etc. 26, 55, 58. The concept of a computationally secure scheme is that theoretically possible to crack such a system, but practically impossible to do so. The balance is simple to comprehend. If breaking a system costs more than the value it protects, then doing so is pointless. The strength of any cryptography algorithm depends on the computational time and effort required to break the algorithm. Cryptanalysis and brute force techniques are commonly used for breaking the cryptography algorithm. Cryptanalysis is the science of breaking cryptography using mathematics and algorithms. Brute force means that you enumerate overall possibilities until you find the solution you were searching for. The assumption of cryptography algorithm assumes to be secure if it is proven mathematically that to break the algorithm requires huge computational resources and time, which is practically not feasible. There is continuous growth in computational power, and accordingly, the cryptography algorithms are also modified to maintain the strength. Most of the cryptography algorithms used today are resilient against classical computer. A quantum computer is new computational technology that is completely different than a classical computer. A quantum computer is much faster than a classical computer. Quantum computing is the next revolutionary technology. It is a technology that will have the ability to reduce the computing time from years to hours or even minutes. The power of quantum computing will be a great support for the scientific community. However, it also poses a serious cybersecurity threats. Most of the existing cryptography algorithms are theoretically vulnerable to quantum computing. A practical quantum computer with sufficient numbers of qubits will be able to break all the modern public key cryptographic systems. 6. Quantum computing. A quantum computer is no longer a hypothetical idea. As quote many experts, it is the world's most important technology, and the race among countries to get supremacy in quantum technology will begin. A quantum computer of a sufficient number of qubits and fault tolerance. US, China, France, the UK, Germany, and Russia are frontrunners in the race, whereas other countries are putting their best effort to join the league. Race to hold control over quantum computing technology is not only limited to country, it is significantly driven by the top technology giants like Microsoft, IBM, Google, D-Wave, Toshiba, etc. Quantum computing got popular after the publication of the essay Simulating Physics with Computer by American theoretical physicist Richard Feynman, 41. In the article, Feynman suggested the use of quantum states for calculations. Quantum computing is an application of a quantum mechanism that uses a quantum phenomenon to perform computation. A quantum computer is a device that performs quantum computing. It manipulates the states of qubits in a controlled way to perform algorithms. A qubit or quantum bit is the quantum mechanical analog. Fig. Performance of classical versus quantum algorithms for prime number factorization. Effect of Shor's and Grover's algorithms on cryptography algorithm. Fig. 6. Theorem, Mosca. 1. Effect of quantum computing on common cryptographic algorithms.
Topographic, rhythm, type, purpose, impact from large-scale quantum computer, symmetric, key, encryption, larger key sizes, needed. 2. SH3 dash hash functions, larger output, needed. Public key, signatures, key, establishment, no longer secure. A. ECDH, elliptical curve, cryptography. Public key, signatures, key, exchange, no longer secure. B. Finite field, cryptography. Public key, signatures, key, exchange. Array 15, 2022. D. 1. The qubits can be simultaneously both at 0 and 1. Quantum entanglement is a strange phenomenon. Quantum computers are built the following features of quantum states. Superposition. Quantum systems can exist in two states at once. A qubit can be in 0 and 1 at the same time, when the measure. Entanglement. It is a quantum mechanical phenomenon. The state of entangled particles can be described with reference each other. Measurement performed on one entangled particle will immediately influence the other entangled particle, respective of the distance among the entangled particle. 3. Interference. The fundamental idea in quantum computing. Array 15, 2022. 4. Key usage analysis bytes per algorithm of open quantum-safe code-based cryptographic algorithms. Key encapsulation mechanisms. Algorithm. Keygen, max heap. Keygen, max stack. Ncaps, max heap. Ncaps, max stack. Decaps, max heap. Decaps, max SAS. L1, x864. 11,420, 90,552, 12,545, 25,720, 12,577, 73,464. L3, x864, 17,844, 179,448, 20,511, 50,026. 20,543, 144,952. C-Meclease 348,864, X864, 271,748,
2,205,032, 276,566, 3,824, 271,940, 43,232. C dash mech lease 348,864F X864 271,748 2,205,032 276,566 3,824 271,940 43,232. C dash mech lease 348,864F X864 271,748 2,205,032 276,566 3,824 271,940 43,232. C dash mech lease 348,864 165,037 4,768,800 23,314 536,300 23,527 73,260. Cups 128 X864 8,114 40,120 13,329 50,320 13,323 62,870. Cups 192 X864 13,260 107,100 22,340 160,100 22,514 125,340. Cups 256 X864 18,760 180,200 33,190 226,200 33,313 255,700. Fig. 8. Keygen operations per second per algorithm. Key encapsulation mechanisms using code-based algorithms.
Array 15, 2022, superposition allows controlling the measurement of a qubit toward a desired state or set of states. The timescale of quantum computing development and quantum computing field is growing rapidly. Globally, there is exponential growth in this field. Building a quantum computer with R qubits and precise error control is the sole objective of the researchers. There are remarkable achievements in the last 22 years in this field. Fig. 1. MIT, Oxford, Berkeley, and IBM could develop a 2-qubit system. The development of the quantum computer can be divided in 3 generations. A. First generation. The first-generation quantum computer was developed at the early stage for non-commercial use. Models were built for proof of concept with low to mid complexity. B. Second generation. Many organizations who got the breakthrough in their initial research and possessed the necessary hardware infrastructure could develop the quantum computer with a higher number of qubits and complexity. The second-generation quantum computers are solely designed and Array 15, 2022. 5. Me analysis of open quantum-safe multivariate quadratic equations-based cryptographic algorithms. Algorithm. Name. Current. Status. Open source C library for quantum-safe cryptographic algorithms. Usage. NIST. Level. Algorithms. Name. Public key size, bytes. Private key size, bytes. Rainbow. Finalists. 1. Rainbow I Classic, 161,600, 103,648. Digital signature. Algorithms. Rainbow I Circumzenithal, 60,192, 103,648. Rainbow I Compressed, 60,192, 64. 3. Rainbow 3 Classic, 822,800, 626,048. Rainbow 3 circumzenithal, 264,608, 626,048. Rainbow 3 compressed, 264,608, 64. 5. Rainbow 5 classic, 1,930,600, 1,408,736. Rainbow 5 circumzenithal, 536,136, 1,408,736. Rainbow 5 compressed, 536,136, 64. Gems. Alternates. 1. NA, no implementation by Open Quantum Safe Project, 352,180, 32. Digital signature. Algorithms. 3. 5. 6. Me analysis of open quantum safe multivariate quadratic equations based cryptographic algorithms. Digital signature algorithms. Algorithm. Key pair, cycles. Sign, cycles. Verify, cycles. Rainbow Eye circumzenithal, X864. 6.06, 412,509,871. 530.3, 4,704,848. 445.7, 5,609,620. Rainbow Eye Classic, X864. 6.77, 369,413. 500, 4,904,751. 500.7, 4,993,920. Rainbow Eye Compressed, X864. 6.02, 415,229. 13.77, 181,591. 445.9, 5,607,009. Rainbow 3 circumzenithal, X864. 0.43, 1,535,117. 54.95, 45,496,023. 49.0, 50,968. Rainbow 3 Classic, X864. 0.49, 815,345. 54.82, 45,059,192. 50.58, 49,416. Rainbow 3 Compressed, X864. 0.43, 1,526,570. 1.92, 2,709,453. 49.2, 50,843. Rainbow V circumzenithal, X864. 0.15, 3,612,337. 24.87, 105,196. 22.36, 111,797. Rainbow V Classic, X864. 0.17, 1,503,322. 23.78, 105,150. 22.42, 103,104. Rainbow V Compressed, X864. 0.15, 3,663,298. 0.32, 3,503,144. 21.43, 116,677. Size use analysis, bytes per algorithm, of open quantum safe multivariate quadratic equations cryptographic algorithms, digital signature algorithms. Algorithm. Keygen, sign, verify, max heap, max stack, max heap, max stack, max heap, max stack. Rainbow Eye circumzenithal, X864. 168,800, 142,400, 172,800, 900, 168,170, 324,300. Rainbow Eye Classic, X864. 269,400, 178,600, 274,300, 900,
174,400, 324,000. Rainbow Eye compressed, X864, 64,400, 160,400, 164,400, 324,300, 64,400, 324,300. Rainbow 3 circumzenithal, X864, 0.43, 1,535,117, 1,535,117, 1,535,117, 1,535,117, 1,535,117, 1,535,117. Rainbow 3 Classic, X864, 0.49, 1,815,345, 1,815,345, 1,815,345, 1,815,345, 1,815,345, 1,815,345. Rainbow 3 compressed, X864, 0.43, 1,526,570, 1,526,517, 1,526,517, 1,526,517, 1,526,517. Rainbow V circumzenithal, X864, 0.15, 3,612,337, 1,940,400, 1,940,400, 1,940,400, 1,940,400, 1,940,400. Rainbow V Classic, X864, 1,343,400, 123,400, 134,400, 134,400, 134,400, 134,400. Rainbow V compressed, X864, 540,300, 140,400, 140,400, 140,400, 140,400, 140,400. Rainbow 7, Resource Use Analysis, Bytes per Algorithm of Open Quantum Safe Multivariate Quadratic Equations Cryptographic Algorithms, Digital Signature Algorithms. Algorithm, keygen, keygen, sign, sign, verify, keygen, max heap, keygen, max stack, sign, max heap, sign, max stack, verify, max heap, verify, max stack. Rainbow Eye circumzenithal, X864, 168,800, 142,400, 172,800, 900, 172,400, 324,300, 164,400, 324,300. Rainbow Eye Classic, X864, 269,400, 178,600, 274,300, 900, 174,400, 274,300, 164,300. Rainbow Eye Compressed, X864, 0.43, 1,526,517, 1,526,517, 1,526,517, 1,526,517, 1,526,517. Rainbow 3 circumzenithal, X864, 0.43, 1,535,117, 1,535,117, 1,535,117, 1,535,117, 1,535,117. Rainbow 3 circumzenithal, X864.
Array 15, 2022. Fig 13. Sign operations per second per algorithm. Digital signature using multivariate quadratic equations-based algorithms. Fig. 14. Verify operations per second per algorithm. Digital signature using multivariate quadratic equations-based algorithms. Array 15, 2022 can be rented out for higher computing demand, just like cloud computing, to serve on a demand basis. Third generation. Third generation will be true quantum supremacy, as the exponential growth and development will bring down the hardware cost. The quantum computer will be affordable and easily accessible to the mass. The third generation quantum computer will bring the viable solution across a wide variety of non-commercial applications, and it will outperform the classical computer and applications. There are many technological challenges to the development of quantum computer with a higher number of qubits. Initially, the through research in quantum computing was considerably slow, took significant time to realize the working model. However, in the recent years, there is an unprecedented development. Scientists around the world are addressing various challenging issues to develop an achievable quantum computer with higher accuracy, 114861. Gartner timeline is to be believed, society will witness quantum supremacy very soon. Though envisioning the future shows a very achievement for the computation field, it is a sign of a storm for security. The development of quantum technology is good news for humanity, as it will uplift our life. However, it also raises a serious threat to cybersecurity, requiring a change in how we encrypt our data. As MIT Technology Review highlights, 20 million qubit quantum computers could break a 2048-bit number in a mere 8 hours. 8. Though the million qubit quantum computers currently do not exist, we need to be prepared and stay ahead of the threat. We can't wait until powerful quantum computers start breaking our encryption. It will be too late. It is time to critically analyze the post-quantum threat and prepare accordingly. 85, 87, 90. We need to identify the research and make a strategic plan to breach the gap. 4. Post-quantum encryption problem. 8. Based quantum-safe cryptographic algorithms. Algorithm. Name. Current status. Open source C library for quantum-safe cryptographic algorithms. Libox. Usage. NIST. Level. Algorithm's name. Public key size. Bytes. Private key size. Bytes. SPHINCS plus. Alternates. 1. SPHINCS Haraka 125F robust. 32. 64. Digital signature algorithms. SPHINCS Haraka 125F simple. 32. 64. SPHINCS Haraka 125S robust. 32. 64. SPHINCS Haraka 125S simple. 32. 64. SPHINCS/SHA-12F robust. 32. 64. SPHINCS/SHA-12F simple. 32. 64. SPHINCS/SHA-12S robust. 32. 64. SPHINCS/SHA-12S simple. 32. 3. SPHINCS Haraka 192F robust. 48. 96. SPHINCS Haraka 192F simple. 48. 96. SPHINCS Haraka 192S robust. 48. 96. SPHINCS Haraka 192S simple. 48. 96. SPHINCS/SHA-12F robust. 48. 96. SPHINCS/SHA-12F simple. 48. 96. SPHINCS/SHA-12S robust. 48. SPHINCS/SHA-12S simple. 48. 96. SPHINCS Haraka 192F robust. 64. 120. SPHINCS Haraka 125F simple. 64. 120. SPHINCS Haraka 192S robust. 48. 120. SPHINCS Haraka 192S simple. 64. 120. SPHINCS/SHA-12F robust. 64. 120. SPHINCS/SHA-12F simple.
64. 120. SPHINCS/SHA-12F robust. 64. SPHINCS/SHA-12F simple. 64. SPHINCS Haraka 125F robust.
Difficult to interpret it unless and until it is decrypted using the encryption key 273386. Most of the encryption algorithms are based on complex mathematical function, Fig3, which is easy to compute in one direction but very difficult to compute in the reverse direction, 23. These algorithms are known as one-way functions. RSA is one of the most commonly used encryption algorithms which makes use of the one-way function. Core strength of the RSA algorithm is based on prime factorization as a method of one-way encryption. The sender uses an encryption key which is generated using the multiplication of two randomly generated large prime numbers. The receiver can decrypt the message only if knows the exact prime factor. The problem is easy to encrypt in one direction but difficult to compute in another direction. Suppose we want to factor an integer n with d decimal digits. The brute force algorithm goes through all primes p up to the square root of n and checks if p divides n. The worst-case time complexity of the brute force algorithm is approximately the square root of n, which is exponential in the number of digits. The quadratic sieve algorithm constructs integers a, b such that a squared minus b squared is a multiple of n. Once such a combination of a, b is found, one checks whether have a and plus b common factors with n. The quadratic sieve is very effective in its asymptotic runtime complexity in the square root of d. The generic factoring field sieve, the most efficient classical factoring technique, devolves an asymptotic runtime exponential in b1/3. The traditional factoring method's usefulness is limited to numbers of a few hundred digits due to exponential runtime scaling. Shor's factoring algorithm, on the other hand, has a runtime polynomial in 1994. Peter Shor developed a polynomial-time quantum computer algorithm for integer factorization. It was a major breakthrough to supremacy over a classical computer, 36. Shor's algorithm will greatly reduce the prime factorization time. An encryption algorithm which is based on the assumption that extracting the private key is computationally infeasible with the existing computing resource does not stand. Successful implementation of Shor's algorithm could easily break most widely used cryptographic algorithm, such as RSA, elliptic cryptography, ECC, and Diffie-Hellman. These algorithms play a crucial role in data protection and privacy. Any possibility to break the algorithms is a serious threat and could be devastating. 15/21/73. Be a direct threat to the information and communication security of individuals, government, and business organizations. In 1996, Love Grover developed an algorithm using quantum computers to search the unsorted database. Grover's search algorithm can find an element in the unsorted database of n elements in root n search. The algorithm can search and find the key in very less iterations. For example, Grover's search algorithm needs only 185 searches to find the password for the DES algorithm, which relies on a 56-bit key. The search algorithm of Grover is not so fast as Shor's algorithm, but it is a potential threat to the symmetric cryptography algorithm. If a quantum computer of sufficient size and fault tolerance is built, then Shor's algorithm will break today's public key cryptography. Variants of the algorithm are applied to both the discrete logarithm problem, Diffie-Hellman algorithm, and open quantum-safe hash-based cryptographic algorithms, digital signature algorithms. Array 15, 2022. Sense of urgency, described by Dr. Michelle Mosca, 47. The urgency for any organization to transit to the quantum-resistant or quantum-safe cryptography depends on the following parameters. Self-lifetime, X years. Number of years you need your cryptographic key to remain secure and your data to be protected. Integration time, Y years. Number of years required to develop, deploy, and migrate to the quantum-safe solution. Threat timeline, Z years. The number of years before large-scale quantum computers will be built which can break the current cryptography algorithms. The threat timeline is shorter than the sum of shelf lifetime and integration time, i.e.,
x plus y greater than z, then it is a matter of serious alarm, as the organizations will not be able to protect their assets for required years against quantum attack. 5, 62, 65. Assessing the exact threat timeline, i.e., value for z, is a challenging task, as there are so many obstacles in building the quantum computer with a required number of qubits and efficiency. However, the current trend in research and development shows that the days are not far away when we will have quantum computers with the required computation power. 9, 19, 50. At some point, we can also expect Moore's law to support the scaling up of the development of quantum computer technology as it happened with conventional computing technologies. Harvesting the encrypted messages with envisioning that they will be able to decrypt these messages when the quantum computing resources will be available in the future. If today's private messages get disclosed even in the future, it will have a serious adverse effect on corporate, government, the military, and the diplomatic relations of countries. So, the threat is not in the future, as shown by Moskatha, but has already begun from the very first day when Shor's algorithm was introduced in 1994. Hence, any communication done since 1994 using an existing cryptography algorithm that is not quantum safe is vulnerable and can be exposed in the future. 7, 63. 4.3. Quantum computing impact on existing cryptography algorithm. A practical quantum computer with the required number of qubits, millions of qubits, will be able to break all the modern public cryptographic systems. National Institute of Standards and Technology, NIST, 2016 report on post-quantum cryptography, shown in Table A, highlights the impact of quantum computing on common cryptography algorithms. NIST is rigorously working to analyze, test, and validate post-quantum algorithms, and is expected to release a draft standard in 2023. The potential algorithms are evaluated on various factors such as robustness against cryptanalysis attacks, algorithm efficiency, interoperability, implementation feasibility, etc. 5. Global initiatives and standardization. 10. The Reggie-Hughes analysis, bytes per algorithm, of open quantum-safe hash-based cryptographic algorithms, digital signature algorithms. Keygen, sign, verify, max heap, max stack, max heap, max stack, max heap, max.
Accredited organizations have taken an initiative in the design, develop, testing, and migration strategy for quantum-safe algorithms 56. Working group, forum, and standard organizations are publishing work, policy documents, white papers, technical details, standardization documents, and cost-effective migration strategies to quantum cryptography. Some of the organizations leading the standardization process are National Institute of Standards and Technology, NIST PQC Standardization. The major initiative has been taken by the National Institute of Standards and Technology to solicit, evaluate, and standardize the quantum-resistant public key cryptographic algorithms. The NIST has begun the process in 2016 to determine the criteria and requirements for quantum-safe algorithms and announced the call for proposal. The first round of submissions was announced in 2017, in which 82 submissions were received, out of which 69 were announced as first-round candidates. Analysis for the first round of candidates was done in 2018, and first NIST QPC Standardization Conference was held. The second NIST PQC Standardization Conference was held in the year 2019, and 26 candidates were announced for the second round. The NIST announced 7 finalists and 8 alternate candidates during the third round in the year 2020. NIST completed the third round process in July 2022. 4 algorithms have been selected. Plausible timeline for NIST PQC standards development, adoption is shown in Fig 7. 2. The European Telecommunication Standards Institute, ETSI. The European Telecommunication Standards Institute, ETSI, has a cyber quantum safe cryptography, QSC, group actively working on post-quantum safe algorithms. The working groups aim to recommend a quantum-safe cryptography algorithm and its implementation. The focus is on architectural consideration for specific applications, implementation capabilities, etc. The group has published cost-effective migration strategies to post-quantum cryptography and solve the challenges and recommendations. ETSI is also organizing workshops on post-quantum cryptography since 2013.
3. The Internet Engineering Task Force, IETF. The Internet Engineering Task Force is focused on promoting voluntary Internet standards. IETF has Crypto Forum Research Group, CFRG. The CFRG Forum bridges the gap between industry and research organizations, bringing new cryptographic technologies to the Internet community and promoting an understanding of the use and application of these mechanisms via information RFCs. The working group is developing request for comment, RFC, protocols compatible with post-quantum cryptography. 4. The American National Standards Institute, ANSI. Accredited Standards Committee X9F, which is the subcommittee. Array 15, 2022. Algorithms as far back as 2010. The X9 committee is working actively on methods to minimize or eliminate avenues of attack by quantum computers on the financial services industry. The working group's objective is to determine what preventative measures the financial service industry should be taking to protect against attacks from a large-scale quantum computer and publish periodical reports and white papers. Federal Office for Information Security, BSI. In order to be prepared for future risk, the German Federal Office for Information, BSI, has also released technical guidelines that recommend algorithms and key lengths and make specific recommendations for Merkle-based signature schemes and XMSS. The focus is the development of quantum-safe public key cryptography algorithms. In 2020, the BSI also developed the initial recommendations for the migration to post-quantum cryptography. Potential solution for post-quantum encryption challenges. Scientists and research organizations are working very hard to develop and standardize quantum-safe cryptographic algorithms. However, not much information is available in the public domain except the work done by NIST. The NIST process to solicit, evaluate, and standardize the quantum-resistant cryptographic algorithms is very thorough, and detailed information is published. Hence, decided to do comparative analysis of 7 finalists and 8 alternate quantum-resistant algorithms, feasibility of the prospective algorithms based on their CPU cycles. Array 15, 2022. Meaning problem for the attacker to recover the message without knowing how to factor in the public key. There are various code-based cryptography algorithms available, among which some potential quantum-safe algorithms are. Classic McSeals was introduced by Robert McSeals in 1978. It is a code-based algorithm proposed for the key encapsulation mechanism. There are very few changes in the algorithm since it was introduced. The changes in the algorithm security parameters are done to increase the computational speeds. Classic McSeals parameters can be set to match all the 5 NIST security levels. The computation time of the Classic McSeals algorithm is extremely fast, but the algorithms require a very large public key size. BIKE, bit flipping key encapsulation, is a code-based key encapsulation mechanism. It is based on quasi-cyclic moderate density parity check QCMDP codes that can be decoded using bit flipping decoding techniques, 68. BIKE can satisfy the NIST security levels 1 and 3. HQC, Hamming quasi-cyclic, is a code-based public key algorithm designed to provide security against classical and quantum computers. The HQC algorithm is designed to achieve NIST 1, 3, and 5 security levels, 51. Classic McSeals is a round 3 finalist, whereas BIKE and HQC are listed as alternate candidates by NIST, Table 2. Runtime behavior and memory consumptions of Classic McSeals, BIKE, and HQC are 6.2. Multivariate quadratic equations-based cryptography. A multivariate quadratic equation-based public key cryptosis having a set of quadratic polynomials over a finite field. In sum, those polynomials could be defined over both grounds and extension field. The security of a multivariate public key cryptosis is based on the fact that solving the multivariate polynomial equations is proven to be NP-hard or NP-complete. Cryptographic algorithms on multivariate quadratic equations, which are potentially quantum safe, are as follows. Rainbow algorithms belong to the family of multivariate public key cryptosystems. It is designed by Jin-Tai Ding and Dieter Schmidt in 2004. The algorithm is based on the oil vinegar signature scheme invented by Jacques Patarin. The algorithm is based on the fact that solving a set of random multivariate quadratic systems is an NP problem, 2072. The algorithm can be used for digital signature, and its parameters can be set to achieve NIST security levels 1, 3, and 5. GMSS, a great multivariant short signature, is a multivariant-based signature scheme producing small signatures. GMS is based on the hidden field equations cryptosystem using minus and vinegar modifiers, i.e. HSEV. The algorithm has a medium-large public key, and it has a very fast verification process. Rainbow is announced as a finalist for round 3, and GMS is announced as an alternate, table 5. The runtime behavior and memory consumptions of the Rainbow algorithm are shown in table 6, table Fig 18. Verify operations per second per algorithm, digital signature using hash-based algorithms.
Array 15, 2022. There, the detailed performance analysis for GMS is available on S official website 44. Hash-based cryptography. Merkle signature. It combines a one-time signature with the Merkle. The hash-based signature, HBS, is a collection of many one-signature OTS schemes. HBS uses a tree data structure to combine many OTS in an efficient manner. To sign a message, an HBS chooses a single OTS from its collection and uses it to sign the message. 29. Fig 19, memory consumption, bytes per algorithm, digital signature using hash-based algorithms. 11. DY-based quantum-safe cryptographic algorithms. Failed. Algorithm name. Current status. Open source C library for quantum-safe cryptographic algorithms. Usage. NIST level. Algorithm's name. Public key size, bytes. Private key size, bytes. Psych. Alternates. 1. SID P434, 330, 28. Key encapsulation mechanism. SID P434 compressed, 197, 28. Psych P434, 330, 374. Psych P434 compressed, 197, 350. 2. SID P503, 378, 32. SID P503 compressed, 225, 32. Psych P503, 378, 434. Psych P503 compressed, 225, 407. 3. SID P610, 460, 39. SID P610 compressed, 274, 39. Psych P610, 460, 524. Psych P610 compressed, 274, 491. 5. SID P751, 564, 48. SID P751 compressed, 335, 48. Psych P751, 564, 644. Psych P751 compressed, 335, 602. Array 15, 2022. 12. Memory analysis of open quantum-safe isogeny-based cryptographic algorithms. Key encapsulation mechanisms. ITHM. Keygen. Keygen. Encaps. Encaps. Decaps. Decaps. Cycles. 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 P434, X8664. 109.63, 280,106, 53.61, 466,265, 135.2, 184,800. P434 compressed, X8664. 57.09, 437,123, 38.69, 661,677, 119.7, 208,859. P503, X8664. 318.89, 704,371, 155.4, 16,856. 391.2, 638,963. P503 compressed, X8664.
166.44, 150,023, 111.7, 23,569, 330.9, 755,004, P610, X8664, 30.91, 808,865, 15.93, 156,924, 37.1, 663,111, P610 compressed, X8664, 18.88, 132,475, 13.28, 188,569, 36.07, 693,106, P715, X8664, 104.79, 23,858, 50.17, 49,823, 127.4, 196,244, P715, compressed, X8664, 55.93, 44,673, 36.75, 68,309, 114.3, 218,073. Fig 20. Keygen operations per second per algorithm. Key encapsulation mechanisms using isogeny-based algorithms. Array 15, 2022. Hinks Plus is a stateless hash-based signature scheme. It is an improved version of Sphinx, especially aimed to reduce the nature size, 80. The NIST submission of Sphinx Plus proposes 3 different signature schemes: Hinks Plus Shake 256, Hinks Plus SHA 256, Hinks Plus Haraka. Hinks Plus is announced as an alternate by NIST in the 3rd round of algorithm selection, Table 8. The algorithm can be used for digital signatures and can satisfy the NIST 1, 3, and 5 security levels. Runtime and memory consumptions of Sphinx Plus are shown in Fig 9, Table 10, and graphically represented in Fig 16, Fig 17, Fig 18, and Fig 19. 6.4. Isogeny-based cryptography. It is a relatively new technique that has begun in the years. Isogeny-based cryptography uses maps between elliptic curves to public key cryptosystems. The security of isogeny cryptography is based on so-called supersingular isogeny problems, or, in other words, finding the isogeny mapping between 2 supersingular elliptic curves with the same number of points. The isogeny-based protocols require a very large key compared to any other post-quantum cryptography candidates. is the one quantum-safe algorithm belonging to IC cryptography family. 30, 40, 82. SIK, supersingular isogeny key encapsulation, is an isogeny-based key encapsulation algorithm. The algorithm implementation is pictured in Fig 21. Incaps operations per second per algorithm, key encapsulation mechanisms using isogeny-based algorithms. Fig 22. Decaps operations per second per algorithm, key encapsulation mechanisms using isogeny-based algorithms. Array 15, 2022 is the smallest public key size, but it is also one of the slowest algorithms. Place in the NIST 3rd round, Table 11. However, it is declared alternate candidate, not the finalist. The runtime behavior and memory. Figure 23. Memory consumption bytes per algorithm, key encapsulation mechanisms using isogeny-based algorithms. 14. Based quantum-safe cryptographic algorithms. Algorithm name. Current status. Open source C library for quantum-safe cryptographic algorithms. Usage. NIST. Level. Algorithm's name. Public key size, bytes. Private key size, bytes. Crystals Kyber. Finalists. 1. Kyber 512. 800. 1632. Key encapsulation. Mechanisms. Kyber 512-90s. 800. 1632. 3. Kyber 768. 1184. 2400. Kyber 768-90s. 1184. 2400. 5. Kyber 1024.
1568, 3168, Kyber 1024-90s, 1568, 3168, NTRU, finalists, 1, NTRU HPS 2048-509, 699, 935, key encapsulation, mechanisms, 3, NTRU HPS 2048-677, 930, 1234, NTRU HRS 701, 1138, 1450, 5, NTRU HPS 4096-821, 1230, 1590, Sabre, finalists, 1, Lightsaber Chem, 672, 1568, key encapsulation, mechanisms, 3, Sabre Chem, 992, 2034, 5, Fire Sabre Chem, 1312, 3040, Frotochem, alternates, 1, Frotochem 640-AES, 9616, 19888, key encapsulation, mechanisms, Frotochem 640-Shake, 9616, 19888, 3, Frotochem 968-AES, 15312, 31296, Frotochem 968-Shake, 15312, 31296, 5, Frotochem 1340-AES, 21050, 43088, Frotochem 1340-Shake, 21050, 43088, NTRU prime, alternate, 1, NTRU NTRP 653, 897, 1125, key encapsulation, mechanisms, SNTRP 653, 994, 1015, 2, NTRU NTRP 761, 1039, 1294, SNTRP 761, 1115, 1763, 3, NTRU NTRP 857, 1143, SNTRP 857, 1322, 1999, crystals-dilithium, finalists, 2, dilithium 2, 1312, 2528, digital signature algorithm, dilithium 2-AES, 1312, 2528, 3, dilithium 3, 1952, 4000, dilithium 3-AES, 1952, 4000, 5, dilithium 5, 2564, 4864, dilithium 5-AES, 2564, 4864, Falcon, finalists, 1, Falcon 512, 897, 1281, digital signature algorithm, 5, Falcon 1024, 1793, 1305.
Array 15, 2022. Lattice-based cryptography. Lattice-based cryptography is based on the computational hardness of lattice problems, the basis of which is the shortest vector problem. Here, we are given an input, lattice, represented by an arbitrary, and our goal is to output the shortest non-zero vector in it, 4259. Implied put, the goal of the attacker is to find the shortest vector from the origin when given the basis of a lattice. A zero vector doesn't count as an answer. The space requirement of this algorithm is exponential and can be a problem in practical applications. Lattice-based cryptography provides a promising solution for postquantum cryptography, 6064. The algorithm is relatively efficient in implementation and has very strong security proofs based on worst-case hardness. The potential quantum-safe algorithm based on lattice is as follows. Crystals Kyber encompasses two cryptographic primitives, Kyber, an IND CCA2 secure key encapsulation mechanism, CHEM, and dilithium, a strongly EUFCMA secure digital. Table 15. Summary analysis of open quantum-safe lattice-based cryptographic algorithms, key encapsulation mechanisms. Keygen, S, keygen, encaps, S, encaps, decaps, S, decap. Cycles, cycles, cycles. Kyber Chem, x86x4, 21419.7, 116577, 20312.3, 122807, 21608, 11518. Poco Chem 1344 AES, x86x4, 589424465, 463.18, 5397844, 475.17, 52623. PocoChem 1344 Shake x86x4 200.0 124946 192.3 1299407 192.8 12963 PocoChem 640 AES x86x4 2179 1147 030 1578 1584200 1653 15120 PocoChem 640 Shake x86x4 794 314 801 669.1 373511 719.6 347371 PocoChem 1344 Shake x86x4 200.0 124946 192.3 1299407 192.8 12963 PocoChem 640 AES x86x4 2179 1147 030 1578 158420 1653 15120 PocoChem 640 Shake x86x4 794 314 801 669.1 373511 719.6 347371 Crips RI 1024 x86x4 35936 69446 31185.3 80016 41013.3 60860 Crips RI 1024 90S x86x4 5186.3 48061 45639 54625 67317 37032 Crips RI 512 x86x4 67526 36882 58938 42674 92577.6 26937 Crips RI 512 90S x86x4 8699 2869 81124 30692 135043 1846 Crips RI 768 x86x4 46477 37353 4263 58493 56923 4180 Crips RI 768 90S x86x4 6665 373 53 60583 4111 9681 56 37353 Medicaid Chem x86x4 4498.7 55426 4695 53860 53519.6 4663, UPAL-CIF HPS 2048509, X86X4 14991699936, 6072.3 41464, 7168.3 34737, UPAL-CIF HPS 2048509, X86X4 8829283 6072.3 41464, 7168.3 34737, UPAL-CIF HPS 4096821, X86X4 6555.6 381017, 6072.3 41464, 7168.3 34737, UPAL-CIF HPS 701, X86X4 9552.3 261573, 6072.3 41464, 7168.3 34737, PCR PRI X86X4 2917.7 86015, 2933.3 85077, 32348 7171, PCR PRI X86X4 3265.3 76422, 32352 85325, 32352 8923, PCR PRI X86X4 31496.3 79234, 31307 82886, 32348 9113, PCR PRI X86X4 3098.3 87717, 2795.6 8116 7436, PCR PRI X86X4 3071.3 85325, 2795.6 8660, 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 PCR PRI X86X4 3
Keygen, in caps,
decaps, decap, max heap, max stack, max heap, max stack, max heap, max S, SaberChem, x86-64, 8552, 25744, 10256, 25904, 10288, 27400, CoChem 1344 AES, x86-64, 68832, 88512, 90448, 173352, 90480, 216600, CoChem 1344 Shake, x86-64, 69616, 77352, 91280, 123,720, 90,480, 165,700, CoChem 640 AES, x86-64, 34,160, 43,392, 43,464, 84,008, 43,480, 104,600, CoChem 640 Shake, x86-64, 34,512, 37,896, 91,248, 123,700, 165,700, CoChem 960 AES, x86-64, 51,152, 64,616, 67,088, 128,064, 67,376, 159,400, CoChem 960 Shake, x86-64, 51,932, 55,712, 67,070, 189,568, 67,728, 120,008, PR 1024, x86-64, 13,560, 16,720, 11,344, 21,944, 11,376, 23,450, PR 1024, 90, x86-64, 13,560, 16,160, 11,140, 21,924, 11,440, 21,440, PR 512, x86-64, 11,256, 7,500, 8,240, 11,704, 8,272, 12,510, PR 512, 90, x86-64, 11,256, 7,952, 7,480, 9,720, 7,440, 10,005, PR 768, x86-64, 12,408, 11,600, 9,712, 1,634, 9,744, 1,7460, PR 768, 90, x86-64, 12,408, 11,984, 8,880, 1,004,026, 9,892, 1,538, SaberChem, x86-64, 6,116, 14,776, 7,184, 14,936, 7,272, 15,760, UHPS 2048-509, x86-64, 5,110, 35,744, 6,513, 30,816, 6,563, 29,120, UHPS 2048-677, x86-64, 6,340, 50,944, 6,362, 44,160, 6,734, 41,888, UHPS 4096-821, x86-64, 6990, 64320, 8258, 56288, 8290, 53063, UHRSS 701, x86-64, 6664, 49136, 7934, 42352, 6767, 42120, CoChem x86-64, 7472, 19928, 8592, 20088, 8624, 21210, PR653, x86-64, 6198, 26328, 6763, 25762, 7255, 26,552, 7,327, 27,862, PR653, 90, x86-64, 6,198, 26,328, 6,763, 25,762, 7,255, 26,552, 7,327, 27,862, PR653, 90, x86-64, 6,198, 26,328, 6,763, 25,762, 7,255, 26,552, 7,327, 27,862, PR653, 90, x86-64, 6,198, 26,328, 6,763, 25,762, 7,252, 7,327, 27,862, PR653, 90, x86-64, 6,198, 26,328, 6,328, 6,760.
Array 15, 2022. Small public key, 32. It has different parameters set to match the NIST security levels 1, 3, and 5. Silverman. In 2013, Damian Stale and Ron Steinfeld developed a post-quantum secure version of NTRU. It is based on the 17. Memory analysis of open quantum safe lattice-based cryptographic algorithms, digital signature algorithms. Algorithm. Key pair, sign, verify, cycles, ISIM2 x86-64, 26,417, 94,400, 10,500, 237,700, 29,132, ISIM2 AES x86-64, 44,000, 55,671, 14,407, 173,353, 44,533, 56, ISIM3 x86-64, 16,110, 155,300, 6,506, 384,900, 17,560, 14. ISIM3 AES x86-64, 29,630, 84,225, 9,637, 259,239, 30,118. ISIM5 x86-64, 1,014, 160,000, 5279, 473,037, 10,031, 24. ISIM5 AES x86-64, 19,500, 127,400, 8,141, 306,924, 19,511, 12.
NCRN 1024X864, 40.23, 615,175, 1,462, 172,900, 9,767, 25. NCRN 512X864, 105.05, 23,797, 2,906, 864,860, 19,684, 12. 18. Memory use analysis, bytes per algorithm, of open quantum safe lattice-based cryptographic algorithms, digital signature algorithms. Algorithm. Keygen, sign, verify, max heap, max stack, is SIM2 X864, 12,616, 20,800, 11,580, 49,600, 11,360, 21,590, is SIM2 AES X864, 12,016, 17,040, 15,400, 44,800, 10,520, 14,800, is SIM3 X864, 14,016, 25,065, 14,056, 78,800, 14,345, 24,720, is SIM3 AES X864, 14,016, 20,790, 18,385, 69,420, 13,513, 16, is SIM5 X864, 16,320, 33,084, 17,375, 113,232, 17,115, 30, is SIM5 AES X864, 16,026, 26,930, 21,191, 108,336, 16,313, 20. PROIUM 12. Keygen operations, per second per algorithm, key encapsulation mechanisms using lattice-based algorithms.
Array 15, 2022. The algorithm is resistant to attacks using Shor's algorithm 5989. SAB also belongs to the lattice-based cryptography algorithm family. The security of the algorithm relies on the hardness of the module learning with rounding problem, MLWR. SAB is a simple and efficient algorithm, 3474. The Sabre suite offers 3 security levels: Lightsaber, NIST Level 1, Burr Sabre, NIST Level 3, and eSabre, NIST Level 5. Photochem is based on the algebraically unstructured lattice. The algorithm has fewer parameter restrictions but a large public key size, 43. Photochem is designed for IND-CCA security at 3 levels: Photochem 640, which targets Level 1 in the NIST, Photochem 976, which targets Level 3 in the NIST, Photochem 1344, which targets Level 5 in the NIST. NTRU Prime is an improvised version of the original NTRU, which has eliminated many of the complications of the lattice security review. Crystals-dilithium is based on the fiat-shammer with aborts technique of Lubashevsky, which uses rejection sampling to make lattice-based fiat-shammer schemes compact and secure. 3638. Dilithium claims to have the smallest public key and signature size of any lattice-based signature scheme that only uses uniform sampling. Falcon is a lattice-based signature scheme designed on the theoretical framework of Gentry, Packard, and Vicontonathan lattices, for which no efficient solving algorithm is currently known in the general case, even with the help of quantum computers. 39. Lattice-based cryptography algorithms seem to be the most exciting and quantum safe. The maximum number of algorithms announced by NIST in third round belongs to the lattice-based cryptography family, Table 14. There are 3 algorithms, CrystalsChem, NTRU, and SAB, declared as a finalist for key encapsulation mechanisms, 54.
Crystals-dilithium and Falcon are declared as finalists for digital signatures. Photochem and NTRU Prime have been announced as alternate candidates for key encapsulation mechanisms. The runtime behavior and memory consumptions of the algorithms are shown in Table 15, Table 16, Table 17, and Table 18. The data in Tables 15 to Table 18 has been graphically represented in Figures 24 to 27. 7. Implementation feasibility and migration challenges. Performance analysis of various quantum-safe algorithms show, in general, quantum-safe algorithms require many CPU cycles for all operations, i.e. key generation, encrypt, decrypt, key exchange, and verify, etc. The algorithms also require large to a very large public and private key sizes. The runtime memory consumption of the algorithms is very high compared to the classical cryptography algorithms. The higher CPU cycle and memory usage is constrained to the lightweight systems and devices. The resource constraints can be resolved from Figure 25. Encaps operations per second per algorithm, key encapsulation mechanisms using lattice-based algorithms.
Array 15, 2022. Security is paramount for all types of ICT devices. Hence, the implementation feasibility of quantum-safe algorithms is very important. NIST completed the third round of the process for PQC standardization in July 2022. Considering various performance and feasibility issues, NIST has selected only 4 algorithms for standardization. Figure 19. Additional 4 algorithms have been considered for enhancement and fourth round of evaluation. The selected algorithm under consideration for the advancement and further evaluation in the fourth needs to be upgraded on various performance factors to satisfy the implementation feasibility. Adoption and implementation of these algorithms will depend on various factors such as throughput, latency threshold, key size limitation of current hardware and software, etc. The replacement of classical cryptography algorithms with quantum-safe algorithms will require changes in existing protocol, communication devices, and hardware, such as high processing capacity to accelerate the algorithm performance, code, operating system, etc. NIST is still in the process of finalizing quantum-safe algorithms. It is likely the process will continue to the fourth round of evaluation. Algorithms which are declared as a finalist has acceptable performance but require additional analysis to gain sufficient confidence. Those of the algorithms which are declared as alternate may potentially be standardized based on the high confidence in their security. Currently, the prime objective is to develop a quantum-resistant algorithm to protect from a possible future attack. However, major implementation feasibility issues which require intense effort to overcome are cryptographic infrastructure. Some of their current IT components may become completely obsolete and will require replacement. Existing algorithms, software, and protocol may require redesign and changes. Overall, the entire migration process will add substantial budget overhead to the organization and unavoidable complexity. Scalability issue. Scalability is a challenging issue for most potential PQC algorithms. It is difficult to prove the hardness of the algorithm at scale. For example, lattice-based cryptography, which is one of the popular techniques used for designing quantum-safe algorithms, does manage to scale well but achieves average hardness. There is a trade-off between hardness and scalability. Either can be achieved, but not both. Large key size and speed. Most of the potential PQC algorithms require large to very large key sizes compared to the existing cryptography algorithms. Because of the large key size and complex algorithm, more time is required to encrypt, decrypt, or verify the message at either end. It also requires more storage space on the device and a longer time to establish secure communication. Resource-constrained devices. Smartphones, IoT devices, sensor networks, industrial control systems, and SCADA are some of the most critical components of our infrastructure. In general, these devices have less memory and processing capacity, which poses a challenge for strong security implementation. Post-quantum cryptography algorithms require intense customization and feasibility study for their implementation in the resource-constrained devices. It is tough to maintain the hardness of the cryptography algorithm while satisfying the resource constraints. Figure 26. Decaps operations per second per algorithm, key encapsulation methods using lattice-based algorithms.
Array 15, 2022. Conclusions.
Quantum computer, millions of qubits is required. It is not sure when quantum computer with a scale of 1,000,000 qubit will be available in the common. However, the exponential growth in quantum computer technologies development shows that the storm is approaching very common. The information we communicate today is mostly encrypted using as states themselves might be intercepting and harvesting the encrypted messages with envisioning that they will be able to decrypt these messages when the quantum computing resources will be available in the future. To counter this threat, we need to migrate to post-quantum cryptographic algorithms at the earliest. Migration to post-quantum cryptographic algorithms requires thorough planning and implementation globally. The migration process will require work on the various fronts, including education, training, and awareness. It will require Fig 27, memory consumption, bytes per algorithm, key encapsulation mechanisms using lattice-based algorithms. Fig 28, key pair operations per second per algorithm, digital signature using lattice-based algorithms. R. Array 15, 2022. Opponents. Early preparation will ensure a less costly and effective recovery with minimal disruption. Budget availability. Not applicable. Availability of data and material. Data transparency. Data sharing is not applicable to this article as no new data were analyzed in this study. Availability. Not applicable. SAS approval. Not applicable. Consent for participation. Not applicable. Consent for publication, not applicable. Compliance with ethical standards. This article does not contain any studies with human participations or animals performed by any of the authors. Credit author statement. Manish Kumar, conceptualization, methodology, study design, software, validation, formal analysis, investigation, resources, curation, writing, original draft, writing, review and editing, validation, supervision, project administration, funding acquisition. Fig 29, sign operations per second per algorithm, digital signature using lattice-based algorithms. Fig 30, verify operations per second per algorithm, digital signature using lattice-based algorithms. R. Array 15, 2022. Fig 31. Memory consumption, bytes per algorithm, digital signature using lattice-based algorithms. 19. Algorithm selected by NIST for standardization and fourth round consideration. Algorithms. Selected. Design. Security. Performance. Overall assessment. Selected for standardization. STALS. Initially, it was IND CPA Secure PKE scheme, then boosted to an IND CCA Secure Chem. Strong theoretical security foundation based on lattice cryptography. The performance of Kyber in many different environments is satisfactory. Overall performance of Kyber in software, hardware, and hybrid settings are excellent. Selected for standardization. Al-Saber. Initially, it was IND CPA Secure PKE scheme, then boosted to an IND CCA Secure Chem. Strong theoretical security foundation based on lattice cryptography. The performance of Kyber in many different environments is satisfactory. Overall performance of Kyber in software, hardware, and hybrid settings are excellent. 6. Advancing to the fourth round. Based on binary linear quasi-cyclic moderate density parity check (QCMDP) codes, depends on the difficulty of solving the decisional quasi-cyclic Sinjor decoding (QCSD) and the decisional quasi-cyclic code word finding (QCC) problems. The performance of BIKE would be suitable for most of the applications, as confirmed by several hardware benchmarks. Because of the overall performance of BIKE, it remains under consideration. BIKE. ELISE. Code-based chem. Uses binary GOPA code. Based on the hardness of decoding random codes, as well as distinguishing scrambled GOPA codes from random codes, it has the smallest ciphertext among any of the NIST PQC candidates. NIST is confident about the security of classic McElise, hence it is still under consideration. Based on QC MDP codes and follows an LWE-like encryption protocol.
The security relies on the difficulty of the quasi-cyclic syndrome decoding, QCSD, with parity problem. Bandwidth of the HQC exceeds that of BIC. HQC's key generation, but decapsulation only requires a fraction of the kilocycles required by BIC. HQC is one of the top 2 alternate chems. The overall performance of the HQC is optimal, but still it is acceptable, based on isogenies. The security of cyc follows from the hardness of finding isogenies between supersingular elliptic curves. It has relatively low communication costs. However, performance on embedded devices may be an issue because the time to perform a single key encapsulation-decapsulation. It is relatively new scheme. It seems promising but needs further study. Features: selected for standardization. Stals: lithium. Lattice-based digital signature algorithm based on the Fiat-Shamir paradigm. The security is based on decisional module learning with errors assumption, which suffices to show that the public key does not leak any information about the secret key. It uses pseudo-randomness techniques improve the performance. The scheme does not use floating point arithmetic, which is an advantage. Highly efficient and relatively simple implementation. Chen. Lattice-based signature scheme utilizing the hash and sign paradigm. The theoretical security is based on the proof of unforgeability in the QROM, based on the hardness of the SIS problem over NTR lattices. The verification process is fast and requires low bandwidth. It is the best choice for some constrained protocol scenarios. NIST has confidence in its security. Because of its low bandwidth, it is a preferred choice for certain applications. SPHINS. Stateless hash-based signature scheme. The security of the SPHINS relies on the security of the underlying hash functions used. Key generation and verification is much faster than signing. It is selected for standardization because it provides a workable signature scheme whose security seems quite solid and is based on an entirely different set of assumptions than those of our other signature schemes to be standardized. CAR. Array 15, 2022. Declaration of Competing Interests. The authors declare that they have no known competing financial interests or personal relationships that could have appeared to influence the work reported in this paper. References: N. Public key crypto system based on algebraic coding theory. JPL Deep Space Network Progress 1978, 114-6. Report 42-44, 1978, DSNPR.44.114M. Bibcode. Galejic G, Alperen Sheriff J, Upon D, Cooper, Deng, Q, Kelsey, Liu Yi, Miller, C, Woody, Peralta, R, Perlner, Robinson, Smith, Tone, D. Status report on the second round of the NIST postquantum cryptography standardization process. Mathersburg, MD, National Institute of Standards and Technology, 2020. https://doi.or/10.6028/nist.ir.8309. NIST Internal Report. NIST IR 8309. Galejic G, Upon D, Cooper, Deng Q, Deng T, Kelsey, Lichtinger J, Miller C, Woody, Peralta R, Perlner, Robinson, Smith, Tone D, Liu Yi K. Status report on the third round of the NIST postquantum cryptography standardization process. IST Publications 2022. https://doi.or/10.6028/nist.ir.8413. Algorithms. Open Quantum Safe. openquantumsafe.org/libboqs/algorithms. Accessed 11 June 2021. Al-Thabaidi, Saud Ohud, Doler, Misha. Cybersecurity challenges associated with the Internet of Things in a post-quantum world. IEEE Access 2020 8157356-81 https://doi.or/access.2020.319345 announcing PQC candidates to be standardized plus fourth round candidates. NIST 2022 July 5 retrieved. https://csrc.nist.gov/accessed 6 July 2022. https://csrc.nist.gov/news/PQC candidates to be standardized and round 4.com. Brute, Frank, et al. Quantum supremacy using a programmable superconducting processor. Nature 2019 574 779 505-10. https://doi.or/1158-61-96-66. Archive. Emerging technology from How a Quantum Computer Could Break 1048-bit RSA Encryption in 8 Hours. April 2, 2020. MIT Technology Review www.technologyreview.com/2019-05-30-65724 How a Quantum Computer Could Break 1048-bit RSA Encryption in 8 Hours. Asif. Ramiz. Post-Quantum Crypto Systems for Internet of Things. A Survey on Lattice-Based Algorithms. IoT 2021 2-1-71-91. https://doi.10.3390/IoT0201. Zardarakshak, Reza. NIST announces round 3 candidates. Psych remains. PQ Secure. 27 July 2020. www.pqsecure.com/NIST announces round 3 candidates. Psych remains. Zardarakshak, Reza. WP release 12/20/20. PQ Secure Technologies. February 14, 2020. www.pqsecure.com/whitepaper release 2-1220. Kalamarugan, Singh, Khan, Ganesan, Rajalajan, Post-Quantum and Code-Based Cryptography. Some Prospective Research Directions. Cryptography 2021 5-4-38. https://doi.or/10.3390/cryptography504. Kalamarugan, Chitralekha, et al. Code-Based Post-Quantum Cryptography 2021 https://doi.or/10944.preprints 2021 04.734.v1. Preprints. Maldi, Marco, et al. Code-Based Post-Quantum Cryptography, based on codes, state-of-the-art and open challenges. 2017 AEIT International Annual Conference. 2017 https://doi.or/10.2391/AEIT.2017.8240549. Bananjay, Utsav, et al. Accelerating Post-Quantum Cryptography using an Energy-Efficient TLS Crypto Processor. 2020 IEEE International Symposium Hum Circuits and Systems 2020. https://doi.or/110/ISKS45731.2020.9180055. Barker, William, et al. Getting Ready for Post-Quantum Cryptography, Exploring Challenges Associated with Adopting and Using Post-Quantum Cryptographic Algorithms. NIST Cybersecurity White Paper 2021. https://doi.or/10944.preprint doi.or/10.428021. Bernstein, D. Jung, Satyantansup, Chung, Lang, T. and Redendahl, C. NTRU. https://ntruprime.cry.pt. Retrieved April 21, 2021 from https://ntruprime.cry.pt. Bernstein, D. J. Hielsing, L. Koblek, S. Niederhagen, R. Reinveld, J. Schwabe, P. The Pinix Plus Signature Framework. In proceedings of the 2019 ACM SIGSAC on Computer and Communication Security, CC 19, 2019, 2129 through 2146, https://doi.or/115. Ewells W., Danvers J.P., Hulsing A.T., Long A.T., Panny L., Desangilhem C., Mart N.P., Postquantum Cryptography, Current State and Quantum Mitigation, NISA, 2021, https://doi.org/10.2824/92307. Illett, O., Gilbert H., Cryptanalysis of Rainbow, Lect Notes Compute Sci, 2016, 336-47, https://doi.org/1183-2072-23. Gorgeous Fabio, et al., A Comparison of Security and Its Performance for Key Agreements in Post-Quantum Cryptography, IEEF Access 2020 8-142413-22, https://doi.org/113250, crossref. Hose, J. Costello, C. Dukas, L. Miranov, M. Narig, V. Nikolenko, A. Raghunathan, A. Tabila, D. Frodo, Proceedings of the 2016 ACM SIGSAC Conference on Computer and Communication Security, 2016, https://doi.org/1476749-2978425. Broadbent, Anne, Schaffner, Christian, Quantum Cryptography Beyond Quantum Key Distribution, Des Codes Cryptograph, 2015, 78, 1, 351-82. https://doi.org/11062-015-0157. Buchanan, William, Woodward, Allen, Will Quantum Computers Be the End of Public Key? JLF-CS, CI, T, H, TLS, 2016, 1-1-1-22. https://doi.org/1469757-215. Retrieved, accessed 6 August 2021. https://www.pulsys.lipsix.fr/links/gms-illustrification.pdf from 26. Chen, L. Cryptography Standards in Quantum Time, New Wine in an Old Wineskin. IEEF Security and Privacy, 2017, 15, 4, 51-7. https://doi.org/11msp.2017. 27, Chen, L., Jordan, L., Liu, Y.K., Moody, D., Peralta, R., Paylner, R., Smith, Tone, D. From 2020. Report on Post-Quantum Cryptography, National Institute of Standards and Technology, Gaithersburg, MD, NIST Internal Report, NIST IRR 8105, https://doi.org/10.6028/NIST.IR.8105. 28. Chen, Jia-Jun, Review on Quantum Communication and Quantum Computation. J. Phys. Conf. 2021, 1865-2-02008. https://doi.org/1742-6596. 28. Crossref. 29. Corporation, ISARA, Math Paths to Quantum Safe Security, Hash-Based Cryptography. ISARA Corporation, www.isara.com/blogposts/hash-cryptography.html. Accessed 6 August 2021. 30. Costello, Craig, Supersingular Isogeny Key Exchange for Beginners. Lect Notes Compute Sci 2020-21-50. https://doi.org/1183-2072-23. 31. Cryptographic Algorithm, Glossary, CSRC. ND. https://csrc.nist.gov/glossary/term/cryptographic algorithm. Retrieved April 5, 2022. 32. Crystals, pq-crystals.org. Accessed 5 November 2021. 33. Belitsia, D. et al. Postquantum Cryptography, Challenges and Opportunities, Robust and Secure HW Design. In 2021 IEEF International Symposium on Pulsation and Fault Tolerance in VLSI and Nanotechnology Systems, DFT, 2021, p. 123. https://doi.org/1568301. 34. Donvers, J.P., Karmakar, S., Sinha Roy, S., Verkauterad, F., Saber, Module LWR, Key Exchange, CPA Secure Encryption, and CCA Secure, Chem. 2019, March none. Retrieved https://eprint.iacr.org/2018.230. From 35. Diffie, W., Hellman, M., New Directions in Cryptography, IEEF Transinfo Theory, 22 6 644-54. https://doi.org/11nsp.2016. 36. Dilithium, pq-crystals.org. Accessed 21 July 2021. 37. Don, Jal, et al. Security of the Fiat-Shamir Transformation in the Quantum Random Oracle Model. Advances in Cryptography, Crypto 2019, 36-37. https://doi.org/1183-2072-13. 38. Dukas, L., Kiltz, T., Lapointe, L., Lubashevsky, V., Schwabe, P., Seiler, G., and D. 2018. Crystals-Dilithium, a lattice-based digital signature scheme. IEEA Transactions on Cryptographic Hardware and Embedded Systems, 2018, 1-238-268. https://doi.org/1314.tches.v2018.I1. 39. Falcon-sign.info. Accessed 3 June 2021. 40. Faux, Luca, Day. Mathematics of Isogeny-Based Cryptography, 2017, 0406. Archive 1711.14. 41. Feynman, Richard P. Simulating Physics with Computers. Int J. Therapiz 167467-88. https://doi/bf02650179. 42. Fouquet, P.A., Hofstein, J., Kirchner, P., Lubashevsky, V., Pornin, T., Preston, R., Saylor, G., White, W., Z., N.D., Falcon, fast-forward lattice-based composition signatures over NTRU. Retrieved https://www.di.ens.fr.
Accessed March 2021. https://di.ensf.fr/pressed/publications/falcon.pdf. From 43. Frotochem.org. Accessed 9 July 2021. 44. GEMS, a great multivariate short signature. GEMS, a great multivariate signature. www.polsys.lip6.fr/links/nist/gems.html. Accessed 8 October. 45. Gibney E. Quantum computer race intensifies as alternative technology gains steam. Nature, 2020, 587-7834-342-343. 46. Gisson, Nicholas, et al. Quantum Cryptography, Rev Mod Phys, 2002, 74145-146. Hashtag ODOI/1013/RevModPhys.74.145. Crossref. 47. Global Risk Institute, a methodology for quantum risk assessment. 8 Nov. Global Risk Institute, globalriskinstitute.org/publications/3423. 48. Global Risk Institute, Quantum Threat Timeline Report 2020, 1 Feb. 2021. Risk Institute, globalriskinstitute.org/publications, quantum-threat-timeline-2020. 49. Grover, Love K. A fast quantum mechanical algorithm for database search. Proceedings of the 28th Annual ACM Symposium on Theory of Computing, STOC 96, 1996. https://137814/237866. 50. Gupta, D.S., Ray, S., Singh, T., Kumari, M. Postquantum Lightweight Identity-Based Party-Authenticated Key Exchange Protocol for Internet of Vehicles with Preservation Security. Compute Communications, 2022, 181-69-79. Hashtag ODOI/1016/j.comcom.2021.09.031. 51. Hamming Quasi-Cyclic, HQC, third round version, 2020, January 10, retrieved, https://pqc-hqc.org, accessed, 11 May 2021, https://pqc-hqc.org/doc/falcon-initialization.2020-01.01.pdf. From 52. HelpNet Security, Quantum Computers, How to Prepare for This Great Threat to Information Security. Published, helpnetsecurity.com. Accessed 24 April 2021. https://helpnetSecurity.com/2020-06-quantum-computers-threat. 53. IBM Quantum Composer, ND. https://quantum-computing.ibm.com/composer/docs/IQX/Shor's algorithm. https://quantum-computing.ibm.com/composer/docs/IQX/Shor's algorithm. 54. Bose, J. et al. Crystals, Kyber, a CCA secure modular lattice-based chem, in IEE European Symposium on Security and Privacy, Eurosep, 2018,
P350, https://1010//IEE/IEEE.0018.00032. 55. Joseph D. Misotsky R. Manzano T. Trico J. Pinawaga F.D. Lacombe O. Leichenauer S. Hidari J. Venables P. Hansen R. Transitioning Organizations Post-Quantum Cryptography, Nature, 2022, 605-7909-237-43, hashtag ODOI/1013/FRV @digital.